Suppose we have some data. We have an idea about how the data might have been generated. I'll call it a hypothesis. What are we going to do about testing that hypothesis? Well, we find a function of the data, test statistic. Now, either by elaborate theory, if we have a rich formulation, and people write books this thick about testing hypotheses, or you use some scientific common sense and think of some suitable criterion. And let's suppose that you can arrange that criterion so that small values are good news for the hypothesis and bad news, and large values are bad news. There are other possibilities, such as that all values close to an integer are good news, or you have obviously a two-sided case. But let's just think of the one-sided case. What we then do is get our data and we calculate the probability that our test statistic is greater than or equal to the observed value, and we call that the observed p-value. And for this argument to work, it must be that we can calculate that value numerically to a sufficient approximation. And by numerically, I mean either by theory or by computer simulation. What in this country ought to be called the shoelace, but of course really called the bootstrap. So we do that, and this hypothetical interpretation is clear. If we found a value of 7%, say, it would say, if we were to take these data as just decisive against the null hypothesis, then in 7% of the cases, of the long run of cases in which the hypothesis is true, it will get rejected falsely. That's the operational interpretation. It's not an instruction on how to use the test. It's an explanation of what the test statistic means. And in that sense, a p-value is calibrated by the kind of explanation I've just given, just as in exactly the same way. If you measure your height, what does the value of height actually mean? Well, in the old days, you would have gone to the National Bureau of Standards in the US or National Physical Laboratory in England, and they would have had a standard foot or yard measurement error. Nowadays, or to go to Paris for the standard meter, nowadays it's elaborate physics. It doesn't mean if you go and measure your height, you have to actually go and do that. It's just that that provides a calibration of what the measurement actually means. And I would suggest in the first place, at least, a p-value is a calibrated measure of consistency with a null hypothesis. And its operational interpretation is the hypothetical one that if we were to do so and so, then the consequences would be such and such. So that's the starting point. Then we have to consider the question, is this any use? When are we going to use it? And I think it's helpful, and implicitly the previous speakers have done something very similar. I want to distinguish 4 distinct cases where such an idea can be useful. And the first is closest to the Neyman-Pearson theory. Historically, one has to remember that Fisher introduced significance tests. Neyman and Pearson, with Fisher's approval, thought that the whole idea need clarifying, and they developed over the subsequent years a series of papers, so-called Neyman-Pearson theory, and that's how it arose historically. And the first situation is the closest to that, a two-decision problem. Industrial sampling inspection. Recall that Egan-Pearson was deeply involved for probably 30 years in introducing quality control methods into British industry, very influenced by the work going on at the Bell Telephone Labs at the time. He was a very intent, very serious practical statistician. Let's think, there are other examples. Auditing of accounts by monetary unit sampling, for example. Is this set of accounts accept or reject on the basis of error rates? Routine screening. Patients come in for routine screening, data are collected, some sort of analysis goes on, and the patient is told, come back in a year's time, you seem to be okay, or come back tomorrow for more tests, accept, reject. And one could well argue, well, people do argue, of course, that that's ripe for a treatment by Bayesian decision analysis, introducing both the prior probability that the patient is in need of further testing and some sort of numerical measure of the consequences of a wrong decision and balancing the two in the obvious way. And incidentally, Neyman and Pearson themselves, in 1932, towards the beginning of their work, wrote the Bayesian, it wasn't called Bayesian in those days, it had some Latin name attached to it, probabilities a posteriori. They wrote the Bayesian analysis of this treatment. And if I could interject a personal note, some years later, I suppose it must have been quite recently, 1970, something like that, I asked Egan-Pearson what his view of the current interest in Bayesian analysis was. And he said something like, well, of course, if you can put meaningful prior probabilities into the problem, you should do so. But then in his experience, this very, very rarely happens. And of course, there's a distinction between those Bayesian analyses in which a flat prior is in effect a convenient computational device with no deep significance to it, and situations where the use of independent flat priors is a total and utter complete disaster. One needs to distinguish those. So the first problem is a two-decision problem of the kind I've just described, in which, in the absence of a better treatment, of a better procedure, one tries to find reasonable levels of probability of rejecting a hypothesis that's true, sending a who in fact is okay for further testing, and then the complementary probability of balancing those two in some way. Now, this does have some implications for the choice of sample size in a much broader class of studies. Standard way of choosing sample size for if the comparing the two treatments seems to be to choose a significance level, an alpha, a power, and a power at a pre-specified distance. So you specify 3 parameters and you get the sample size that you need. And it was pointed out, I think probably by Peter Armitage many years ago, that this is a very clumsy procedure. It's not wrong, but it's a very clumsy procedure because it's making you specify 3 things when, in fact, 1 is enough. Or putting it differently, there are many combinations of the alpha, beta, and delta that will give you exactly the same answer. And there's some, it's not a mistake, but there's some clumsiness in doing it that way. But much more seriously is the point that Fisher made somewhere at an earlier stage, that these computations of power, once you have the data, are virtually irrelevant, because you may have low power, and yet by chance your data have come out in a position that gives you reasonably strong decision, or vice versa. You may have high power, but bad luck, your data fall bang in the middle of the indecisive region, and you've got low power. And by contrast, if you specify sample size by the width of confidence interval or a standard error, you can compare the standard error you specify and hope to get with the standard error you actually got. And that can be really quite informative about what really happened. So that was the first possibility, close to the Neyman-Pearson theory, two-decision problem, used significance, test-like formulation used in the absence of a Bayesian possibility of a Bayesian treatment. Second possibility is that the null hypothesis is something you're actually deeply interested in. And a beautiful example of that is the work done some few years ago at CERN, connected with the discovery of the Higgs boson, in which a 25-kilometer tunnel was built linking France and Switzerland, and particles were accelerated around this till they reached close to the velocity of light and were collided in the so-called Large Hadron Collider. And the object there was to did the Higgs boson exist? And of course, if one could have observed the Higgs boson, finding one Higgs boson would have answered the question. But it could only be addressed indirectly by finding the energy of the particles that were being collided and getting a distribution of the energy. So the data took the form of a series of independent Poisson variables with a mean that was changing slowly. And if and only if the Higgs boson exists, one particular cell in this histogram would be high. So data were collected for a considerable length of time, because this was something where it was highly desirable that if a claim was made, it really, really was right. So the physicists insisted on extreme selectivity. They had discussions with statisticians over a good many years over this, because the whole enterprise took 10 or more years to come to fruition. So there were many meetings to discuss the statistics. The physicists' interest listened politely. I'm not sure they were very influenced in the end. They just went for a very cautious level of significance. So that's my second category of problems, where there really is an interest in a serious scientific question. A rather more immediate example might be that you had two medical treatments that you really, really thought their effect on adverse reaction reports would be the same. The null hypothesis would be that the number of adverse reaction reports was exactly the same. Coming in Poisson processes, that the means would be exactly the same, two-sided hypothesis. So those were two quite distinct possibilities. Possibility one, really a two-decision problem. Possibility two, a hypothesis you were really, really, really interested in, that it might be true or near enough true. The third is a so-called dividing hypothesis. I've given an example there, 2 treatments controlling blood pressure. It may well be that there is a difference one way or the other, but you don't really have any particularly strong interest, strong belief in there being the same. But as long as the data are consistent with A equals B, there's no basis for a claim that one is, as it were, superior to the other. There may be other evidence, but there's no evidence from your data that there's anything going on. So as I said, it's better formulated as an interval estimation problem, although the idea that interval estimation could subsume significance testing is, I think, mistaken, because you can produce examples where interval estimation breaks down completely, where, for example, the appropriate intervals, appropriate inference is a set of disjoint intervals, or even is in Feiler's problem, is the outside of an interval. So the significance test idea is appropriate. And then my final category is of issues of model adequacy. You fitted a model, possibly a simple one, possibly a complicated one. There are umpteen things that might go wrong. Non-linearity, correlation errors, severe non-normality, etc., etc. The use of a significance test then is to prevent you from being worried about things that are in fact just potentially random fluctuations. And I think use of tests in those contexts is to be thought of as very largely exploratory, although you might find some dramatic, something that was both highly significant and very big that really had to be dealt with. So the fourth possibility is one of exploration more than final analysis. Then I come to the most important slide and point of all. Can I have the next slide? It's got nothing on it, I should tell you. Dare one stand here in 2018 and not say big data? No, the answer to that. The warning is this, that of course any standard method of analysis applied to big data, the usual statistics will have standard errors going down like 1 over root n. And therefore, if you think even of a simple mean, sigma over root n, if n is 10 to cube, that could be quite small. If n is 10 to the 6th, or 10 to the 7th, or 10 to the 8th, sigma over root n is going to be very tiny. So if you take measures of systolic blood pressure, should we say, an average, a few million of them, and think about the mean of the population you're considering, the confidence intervals seem very, very, very tiny. Is that realistic? I think almost certainly not, for a variety of reasons. And that are to do with essentially not the breakdown of normality or of any distributional assumption, but the breakdown of independence assumptions that hidden within this data are likely to be all sorts of perhaps individually small, but nevertheless cumulatively important correlations, positive correlations in the errors which amount to error inflation, of course. And if there are enough of if you think of the variance of the mean with all these cross-product terms written in, if enough of them are tiny, but there are a lot of them, the net effect is very big. And a special feature of that is what's called self-similarity in probability theory. I have not time to go into that. Can I have the next slide, please? Going back to first principle, I took from almost my first sentence, I implicitly used the word probability. So we have to ask ourselves, what's the meaning of probability and in each particular context? Now, the great Soviet mathematician Kolmogorov axiomatized probability in 1933. He wasn't the first to do so, but his axioms really established probability theory as a beautiful and vibrant part of modern mathematics. But it's interesting that Kolmogorov himself retained an interest in the interpretation of probability, and in that he worked widely. I believe, although it's possible that somebody in the audience would know better than I do, that at his death, he was working with the Swedish mathematician Per Martin Löf on a new concept of probability that was more related to, I think, the logical work of Carnap, people like that. But it's interesting that the two people who, in a certain sense, had most impact from a different point of view on statistics in the 1920s, 1930s, 1940s, Fisher and Jeffreys, they both used two versions of probability. Jeffreys had a kind of probability describing random phenomena, and he called that chance. And he reserved the term probability for a rational degree of belief. And his great book of 1939 was essentially setting out a theory of statistics that was developed from this notion of probability as what a rational person would believe in this hypothesis, given whatever it was they were given. And Fisher had something mysterious, as so much of Fisher's writing is. He had the first sort of probability of just describing simple random phenomena in a coherent way. But he also had the notion of Fisher's notion of a proportion of a hypothetical population. He regarded the data as drawn from a hypothetical population, and he repeatedly stressed the word hypothetical. And what one was really interested in was the properties of that population, what was underlying. And that's similar in spirit to Jeffreys, but Fisher was trying to keep solely within the same mathematical framework as the other. As far as I can tell, Neyman remained solidly empirical frequentist. Towards the end of his life, I think he was puzzled by, towards the end of his life, he became deeply interested in applications over a broad front, having earlier been much more theoretical. I think that changed his views to some extent, but it doesn't appear in his writing. Whereas Jimmy Savage was exclusively personalistic in his view. Probability was what you believe, how strongly you believe, or rather, how strongly you ought to believe in this, given certain information. And there's an interesting parallel in that with the notion of the scientist's individual personal belief in what's going on. And one would know, I expect many of you in the audience know better than I do, that individual scientists do have strong personal beliefs in this or that. But by and large, that is not what we as statisticians deal with, because we're concerned, I think, very largely with communicating conclusions to others in a way that will be intellectually convincing. And so that limits, in my view at least, the interest in, it doesn't limit the interest in Savage's work, but its relevance. I've almost come to the end of my slides. Can I? Well, I was just going to make the point that one tends to think that we set down a beautiful theory and of whatever it might be, and everything follows from that theory. In fact, I think it's, to some extent at least, always a two-way traffic. If the theory is not so good, critical use of it will expose its limitations. And on the other hand, if something is successful in applications, that increases its importance and relevance. Those are trite remarks, but I recall Fisher, I think, my memory is getting defective, but I think I recall Fisher saying once, people work on foundations. They think they're propping up a great building. They're actually mice in the basement. Or he might have said rats, I'm not quite sure. And whether he included himself amongst the mice is not quite so clear. But there's an element of truth in that. Can I go to the next? No, I think I'll skip that. There's not time to go through that, although it is concerned with. Then, no, I'll pass on that. I was going to make a comment about what the interpretation might be of the kinds of p-values that you see in some modern genetic applications, tend to log p of 10, 11, 12 or so, can't possibly be a significance level probability. If it's anything at all, it's an indirect estimate of something. And there's a little note there about that, what that might be. Can I have the next slide, please? Perhaps there isn't one. I don't think there is one. So let me conclude. All I've said really is the p-value idea is a very simple idea. We have a test statistic. Do we find what we expect to find, yes or no? And that has a very clear and simple definition, an appealing definition. How we use it is a multifaceted thing. And some of the confusion in the current discussions, I think, and the pontification that comes, particularly from the other side of the Atlantic, if I dare say so, some of that stems from a confusion between the different objectives that one might have in mind. Thank you very much.